All right, today we are looking at Unit 4, Lesson 7, and this is out of Chapter 12, Lesson 7 from the textbook. The topic of our lesson is graphing trigonometric functions. We're going to start off with a concept for how to graph a sine or cosine function. You can see in the slide here on the left we have the graph of y equals sine theta. And you'll notice that both of these functions they're called wave functions or periodic functions. But they're called, waves because they go up and down, kind of like the waves in the ocean. But a sine graph, you'll notice, starts at the origin, while a cosine graph starts at the number 1. But both of these graphs fluctuate between the values of +1 and -1, so their range for both of them is all y values between -1 and 1. And because they go on forever periodically, the domain is all real numbers, both positive theta values and negative theta values over to the left of the y-axis. The amplitude here for both of these graphs is 1. The amplitude is basically the distance between the theta axis right here, or the y-axis, the theta axis, which is typically the x-axis, and the height of the actual function. So from here, the midpoint up to the maximum is 1, or from here down to the minimum value over here is also a distance of 1. That's what the amplitude is. And we talked about the period in the previous lesson. The period is how long the graph takes to make one complete revolution back to its starting point. And the period for both sine and cosine is 360 degrees, or 2 pi if you're looking at radians. Basically, the graph for sine starts here, goes up, down, comes back. That's what one period is right there. For cosine, we start at 1, we go down to -1, we come back up to 1. And that's the period for the cosine graph. So our first example, we're going to find the amplitude and the period of the graph y equals sine 1/3 theta. So first we're going to find the amplitude here, and what you're going to think about for finding the amplitude is the coefficient on the expression for what y equals. So you have to imagine what number, essentially the amplitude is the number that's in front of the trig function. So the number that's in front of sine here, well, there is no number, so there's an implied value of 1. So the amplitude is 1 in this scenario. The way you find the period is you take the regular period, which is 360 degrees, and you divide it by some b value. And the b value is the value that's directly in front of theta. And if you have copied down the notes from the poster on trigonometric graphs in class, you have the formulas for for how to find amplitude and how to find period. You'll have these written down already, so it's really simple if you have those formulas in front of you. But they didn't present those formulas in the slideshow yet, so it's kind of tricky knowing where on earth did they come up with A and where did they come up with B. But basically that's the formula. So the amplitude is always the number in front of the trig function. The b value is the number that comes after the trig function. To find the period, you do a full circle divided by the b value. 360 divided by 1/3 is 1080 degrees. So this graph takes 1080 degrees to make one complete revolution. Here's a check your progress problem. Go ahead and pause the video, figure out the answers, and we'll look at the answers on the next slide. And this time the answer is A. The way you get the period, you do 360 divided by 1/2, and you'll get 720. And again, the amplitude is the number in front of the word sine, which is just an implied value of 1. For example 2, now we're going to graph the function y equals sine of 3 theta. So the important information that you need to know in order to graph this are the amplitude and the period and the x-intercepts. So again, this time the amplitude is 1 because there's an imaginary implied value of 1 in front of sine. And then the period is 360 degrees divided by this value, 3, which is 120 degrees. So this graph makes one complete cycle in 120 degrees. And again, because it's a sine graph, it's going to start at the origin. It's going to move up. I'm going to trace it with my cursor real quick. It's going to start here. It's going to move up, come down, and come back. That's what a sine graph looks like. So here we're finding the x-intercepts, which is basically the places where the graph crosses the x-axis. And because it always starts at the origin, the first intercept is the origin 0, 0. And then the sine function always has an x-intercept at the midpoint of a full circle. So that's why they have half of the period, half of 360. And since we know that the full period for this function is 120 degrees, half of 120 is at 60. And then at the full period, back to where we end up, is 120. So we're going to have 3 x-intercepts always for a sine function. So you can see our graph here. We have our first intercept at 0 degrees, and they use a scale of 45 degrees here, which I think is kind of confusing. I think it would have been better if they had used a scale of maybe 30 degrees, just to show the increments better. When I do this problem in class, I'm definitely going to use a scale of 30 degrees, so it'll make a little bit more sense. But you can see that the graph returns to the original starting position right here, which is 120 degrees. It makes another revolution, returns to the starting point, which is 240, starts here, makes another revolution, returns to the starting point at 360. So you can see there's 3 full periods in 360 degrees for this graph. And notice again, the amplitude is 1. We start at the theta axis and move up to the maximum. It's 1 unit. From theta axis down to the minimum is 1 unit. The amplitude is 1. Part B, we're going to graph y equals 1/2 cosine theta. This time, our amplitude is 1/2 because there's a 1/2 in front of cosine. The b value is just the number 1, so when we do 360 divided by 1, we just end up with 360. So this graph is going to make 1 full period or 1 cycle in 360 degrees. The x-intercepts happen on a cosine graph at 1/4 of a full period and 3/4 of a full period. So if the full period is 360, 1/4 of 360 is 90, and 3/4 of 360 is 270. So there's 2 x-intercepts. The cosine graph always starts up at the amplitude, or 1/2 for this problem. Then it works its way down towards the minimum, -1/2, at the midpoint of the period. And then it works its way back up to the amplitude at the end of the cycle. And you'll notice that we have x-intercepts at 1/4 of the way, 3/4 of the way. If you think about this, from here to 90 degrees, that's a quarter. From 90 to 180 is a quarter. 180 to 270 is a quarter. And 270 to 360 is a quarter. And that's why they used 90 degrees or 45 degrees as the interval on example 2 part A, just to base it off the quarters of the unit circle. Okay, we've got 2 problems to check your progress. First one is y equals sine 2 theta. Go ahead, pause the video, figure out what the period is going to be, what the amplitude is going to be, and pick your answer. We're going to see the answer on the next slide. The answer this time is A. Because of the 2 theta, that means we're going to have 2 full periods in 360 degrees. So that's why we have 2 graphs here in the full circle, 360. For part B, we're going to graph y equals 3 cosine 2 theta. Go ahead and find your amplitude and your period, and we'll see the answer on the next screen. And our answer this time is A. This is what our graph looks like. The amplitude is 3, so we have to go up to a value of 3 and down to a value of negative 3. So right away, that 3 right there should occlude you in that none of the other options make sense, because here we have an amplitude of 1/3, here we have an amplitude of 1, here we have an amplitude of 1. So none of these other options even make sense. For example 3, we've got a real-world problem now. It's about sound. It says that humans can hear sounds with a frequency of 40 hertz. Find the period of the function that models the sound waves. So basically, the concept of what a hertz is, this word is H-E-R-T-Z. It means that the graph makes 40 cycles per second, or 40 periods, 40 full rotations in 1 second. The period is the time that it takes for 1 cycle, so it's 40 periods every second. So therefore, the period is 1/40, or 0.025 seconds. Part B. We're going to let the amplitude equal 1 unit. We're going to write a sine equation to represent the sound wave y as a function of time t, and then we're going to graph the function. So since our period is 360 or 2 pi over the b value, our period we know from part A is 0.025. This is going to help us solve for the b value. When we isolate b in this problem, we get 80 pi. So our equation is going to be of the form y equals a times sine of b theta. We know the amplitude is 1 and the b value is 80 pi. So our equation is y equals sine 80 pi times t. So then graphing that, this is basically what it looks like. The graph makes 1 full rotation in 0.025, that's the period, and the amplitude is 1, so we go up to 1, we go down to -1, we return to the origin. Again, the sine function always starts at the origin, moves up, then comes down to the minimum value, then returns to the axis, the t-axis in this problem. Okay, we got a real-world problem, very similar to the one we just did. This one's about instruments. Go ahead, pause the video, read through the problem, and work out your answer. We'll see the answer on the next slide. Okay, this time we have a period of 0.02 seconds. And then in part B, we're going to look for the sine equation to represent the sound wave. Go ahead and pause the video, read through it, work out your answer. We'll see the answer on the next slide. Okay, this time our answer is sine 100 pi times t. If you take the full circle, 2 pi, divided by 0.02, you're going to get 100 pi as your answer. We're going to end the video here and pick up with the last few examples in another video.